Okay, so welcome to part two of the silo problem series that we're running here. So just to recap what we did in the first session, we essentially tackled these first four bullets here. And what that looked like was this. We just described things mathematically and then used that to kind of solve through. And then we drew this diagram here. One thing that I maybe should have highlighted in this diagram as well is that actually we're missing the drain, right? We're missing the kind of area through which the liquid is expected to drain. So maybe here you'd highlight something like this. And this distance here would probably be whatever the diameter of that orifice is. So let's just call it, I don't know, DO for now, right? Because we haven't determined it. We're going to determine it in this second section here. So in this video, we're going to cover this fifth bullet here. And like I said in the previous session, I'm not going to spoon feed you here. I'm basically just going to show you how I would approach the problem, and I'm not going to explain every kind of granular detail as I go through. So let's get started. So for starters, as I've established with you guys before, if I imagine this is my silo, let's fill it with some water. If I imagine this is my silo and I'm draining it through this area here, I can say that the energy conversion taking place here is gravitational potential energy being converted into kinetic energy. And if I want to describe this mathematically, I could say, well, GPE is just mgh, and kinetic energy is half mv squared. I can divide through by m here, and I can rearrange for fluid velocity, which gives me this form here. I can then equate fluid velocity to volumetric flow rate over the area through which the liquid is flowing, and I can relate head, or H, to the volume of the water in the tank over the cross-sectional area of the tank. And I can also equate Q, or volumetric flow, to minus dV over dt. I hope I've explained all of those ideas in our in-person session, so I don't need to recap them here. And when I substitute these in, I end up with something that looks a little bit like this, right? dV over dt equals minus A0 or AO root 2G. Let's write this a little bit differently actually. 2G over AC V. And I can, well, look at this and think, okay, well, this is a differential equation. How do you solve differential equations? Well, you might want to have a go at integrating. So first of all, I'm going to move this V over to the other side, as hopefully you'll understand why in just a sec. And that will leave me with something like this. So I'm taking the integral of V to the minus a half. Let's write this out just for clarity actually. Okay, equals minus A0 or AO root 2G over AC. Okay, what I've done here is I've integrated both sides with respect to time, and you'll note on the left-hand side the dt's have cancelled. So in effect, I'm integrating the left-hand side with respect to v and the right-hand side with respect to t. And when I do that, let's see what comes out. So you know the procedure, add 1 to the power and divide by the new power. So I get this, minus A0 root 2g over AC t plus my unknown constant here. Now, there's something we need to understand about this equation we've got here. We've got 2 unknowns in it, right? We've got this plus c, and we've got this a0 here, a0, a o, whatever. How can we solve these? Well, we can introduce our boundary conditions, right? So our boundary conditions in this instance are, we know that let's put that in blue. We know that at t equals 0, v equals 12, because at the time I removed the plug, essentially, my initial volume is 12 meters cubed of water, and that when t is equal to 300, or 5 minutes, my tank is fully drained. So I can say v is equal to 0. And I can essentially plug in these boundary conditions. Before I plug in those boundary conditions, actually, let's make this equation a bit more palatable. So I'm going to divide both sides by 2, and then I'm going to square both sides just to make it so it's just v equals da 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 da, right? So v equals, so I'll have divided this by 2, 2g over ac t plus c over 2, all squared. Okay, so now I can plug in my boundary conditions. Let's have a look at this, this first one here. So when t is equal to 0, v is equal to 12. Okay. Well, if I'm substituting 0 in for t, then this first term here cancels to 0. So I can say that 12, which is my value for v here, is equal to c squared over 4. I can multiply both sides by 4 and square root both sides, which will give me the square root of 48, and that is equivalent to 4 root 3. Okay. This is equal to c, right? So c is 4 root 3. Let's have a look at my second boundary condition here. So t is equal to 300, v is equal to 0. Okay, well, if v is equal to 0, then imagine this v here turning to 0. Then that makes this whole right-hand side equal to 0 here. And we can kind of equate this minus a0 over 2 root 2g over act to c over 2. So I can say down here, well, c over 2, c over 2 is just 2 root 3, because we know that c is 4 root 3 now. So 2 root 3 equals a0 over 2 root 2g over ac, and I can just rearrange for a0 here. So I can multiply both sides by 2 and then divide through by this whole root thing here. So that's just going to be 4 root 3 over the square root of 2g over ac. I'm missing something here. Yeah, I'm missing the t. Right, I'm missing the t. So t is equal to 300 in this instance. So I could just write 300 here. Okay, and when I bung that into my calculator, I get 8.24 times 10 to the minus 3. So that's the area of the orifice that the liquid is draining through. So I can equal that to a0 here. So I've got my value, my unknown values now. So what I'm going to do is I'm going to take this equation that I've got up here, and I'm basically just going to I'm going to substitute my values in and just kind of express this whole term that I'm highlighting here as just a number. just to make it a little bit easier to read and understand. So when I put all the values here into my calculator, this whole coefficient here is equal to minus 0.01155. Let's reintroduce this t here. And then c over 2, well, if c is 4 root 3, then c over 2 is just 2 root 3. And if I square this, then this is all equal to v. Okay. I've magically changed colors here, which wasn't my intention. So this is my final equation, right? This is my final equation here. And if I look at it by inspection, this term here is going to be my intercept, and if I think, well, this is going to square, well, when I square that, that's just going to be 4, because 2 squared is 4, times 3, because root 3 squared is 3, which is 12, and that would make sense, right? Because my initial volume is 12. And here I've got this quite small magnitude negative coefficient here, so that kind of looks promising as well. What I'd expect you guys to do for this problem is to type this into Desmos and maybe present it to me like this. You don't have to use Desmos, but whatever way you can find a way to present a graph to me, that's great. When I look at this graph, let's zoom out. It's a quadratic, as you'd expect. And let's have a look at these intercepts. So you've got an intercept here at 12. So that's basically just saying when time is 0, the volume in the silo is 12. And I've got this intercept here. It's almost equal to 300, right? If I want to visualize this a bit better, I've introduced this f100x here. That's just a graph transform. I've kind of squished it along the x-axis by a factor of 100, and this can kind of help us observe how the fluid drains in the tank. So it starts at 12 here, and as time progresses, the volume in the tank decreases and decreases and decreases until it's got an intercept here of 3, but I've squished it along the x-axis by 100, so that would represent 300 seconds. Okay. So if you presented something like this to me in your email, like I said in my last video tutorial, I'll be a very happy bunny. So there you go.